the bulk of your assignment. So there's supposed to be, previously there's 3 assignments. Now there's only 2 assignments. So there's one big one and one small one whereby you do a little bit of calculation. That's what we're going to cover in the first 2 weeks. After that, right, then we will spend the rest of the 4 weeks, rest of the lesson, right, on this the project itself. Okay, whereby you will be purely application of the software. Okay, so if your application, first thing is I need you to go and download this Abacus software, the student edition of it. You will be using it, okay? Abacus software later. It's okay. Just once I hook up, I can show you. It's okay. Okay, so there's a lot of way you want to that you want to do it. It's fine. Okay, most of the time my preference is to encourage the student get your own laptop. Okay, download the student edition whereby you can try it for free, get familiarized with the software. I'm not very sure how has the syllabus changed, but I teach this module for six years plus. It should be about 6 years. My experience is that this is something a bit different from your previous module, whereby this is actually require you to be very independent. Okay, in the sense that you will need to understand how to use the software on your own, so that we will focus on the application part of it. Okay. So that's why I would recommend you to get your laptop, and you must do it early. You don't wait until the 4th lesson or the 3rd lesson where I have already gone through a lot of the features of the software. Then you start to get, and you start, I cannot download. Then that will be the 5th lesson. Then last lesson that you start to do, then you'll be doing too late. Okay, the exam will also be using the software. The exam will also be using the software. Okay, so that's why I say it will require you to be very, very independent. I haven't shown you the assignment yet. Can you? Okay, that's why there's a little bit of housekeeping first, because I want to say this upfront. Get the laptop, download the software. Okay. Number 2, I write it down. Okay. So it's a laptop, then the Abacus student edition. Number 2, you can also do it right through the RMIT My Desktop. Have you used it before?
Yes.
During your visit, right, the overseas visit, you all use that, correct? Do you all use that?
Yeah.
Those who use it, raise your hand. Okay, you must help me so that I can move on. That means that most of you haven't done it. Then I will explain. I will waste everybody's time. Hey, come on. Who have used My Desktop before? Can you put out your hand so I know? Okay, so I assume, am I correct to assume everybody use it? Everybody know how to use it?
There's one intake here that have not went for the overseas.
Okay, so who have not? Thanks. Who has not used the RMIT My Desktop before? Okay, so no. How many? Put your hand. I can't see your hand. Okay. Is it okay if I will roughly show you later on, but you will need to go and check with the rest of the class? Are you okay? Okay. There's a reason for that. Because under the My Desktop, I need you to also check whether you have this Abacus license or not. Okay. Who have your laptop with you? Anybody have a laptop with you? Those who have your laptop must sign into your RMIT My Desktop.
Thank you.
Hey, hello. Wait, Third thing is I need to go to your Canvas. See whether you can see the module or not. Okay, these 3 things. The reason is because I need you to see whether you have your assignment or not. Today, like I said, this is a very, very fast lesson. You imagine that 6 lessons, supposedly there's 1 virtual, 5 physical, correct? So you move very, very fast. There's 2 assignments. Today I will go through part of the first assignment. The second week, right, you're supposed to, we're supposed to finish it, and I will spend half the lesson to finish it, right? Then you will need to submit your assignment 1 on the We will fix that when we're going to do the date. Later I will show you first your canvas, where is it, okay? So I need to check whether your module is there. That's the three thing. Can? Okay.
maybe 是这个 CAE just now 我看到command 本地人 for I think 是 CAE but I think 我要看他 software 那边有没有给到你 yeah
Okay, so this is the RMIT My Desktop, correct? So you log into My Desktop. maybe 效果比较好 one year
there's only one
So under the desktop, right? Okay, you go on to okay, then you go into your desktop. There's a few things that actually I wanted you to do but I thought that normally we have it at the computer lab, but those that can do it, follow. Can you just go in to the desktop? I want you to look for the software called Abacus.
Which version as well? Which version?
Doesn't matter, any version doesn't matter.
But there's like two kinds, one is CAE, one is command.
Yeah. Go to Abacus CAE. Yeah, no, not the command, go to Abacus CAE. So your student profile must have the software, which I don't know why, but they remove mine. So I need you to check it. Okay, that's the first thing I'm going to check. Yep. The second thing the problem that I don't use this my desktop before. So what's the problem with it? The problem is because you're going to build a model. Doesn't matter whichever edition, just use Abacus in 2023 CAE or 2024 CAE. Not the command. So you can access Abacus, which I'll go through. Okay, when we start the software part, like I say, because these 2 weeks we'll focus more on the calculation part of it. I just want to make sure that you can have it to have what? It's very hard to struggle against your voice, you know. Okay. I just want to make sure that you all have all these things first, so you have to pay back the RMIT if they have time to set up profile. Every year, without fail, there will be students that cannot access it. Okay, do the due diligence, try it at home. Okay, those of you don't have it now. Number one, make sure that you can log on to my desktop. Number two, I need to try the software. Number three, because the problem we're going to build the software, we're going to build the model from my desktop. You need to be able to save it. So you must save it. I can't remember is it a H. Some of it is a H drive, some of it is a K drive. After you've done something to it already, right? There will be your temporary file, whatever you have done so far. Save it, then send it to yourself. Because this you can't accept not fixed over. Right. So I need you to try it now. Okay? Looks like problem, feedback. Okay? Like I said, every year without fail, there's people that can't do it. The student edition, right? It works good, it works well because you can do it this way and it's fast. It's not a little well. It lags, it have a bit lagging, can't be helped. The problem with student edition is that you are limited to, I think it's 1,000 and 1,000, so you can't really do a big model for that. But generally, it's good enough. So that's why I encourage you to do the student edition. Okay? Housekeeping, like I said, this is all housekeeping. Number two, for the canvas. Yes. Hey, hello. Second thing, the canvas, right? I need you to go up to the canvas. Those that, like I say, same thing, those of you can do it. I want to see whether you can see the assignment or not. Because every year, right, the first lesson I will start the class to do the assignment 1 already. Okay? So can you all see the assignment 1? Yep. Huh? Can you see it? This assignment 1, this is 10% of your entire module weightage. This is 10%. Okay? So you're supposed to calculate what's the force when you apply a displacement and what's the force in each of the spring, things like this. Your stiffeness matrix like what? A little bit like, no, generally the same as when you do your structural analysis, generally. But we're going to appreciate why we need to do this in finite element. Because that was really the basis for using a finite element like this. Same engine, this is the first principle. Okay? Can you all, those of you have laptop, can you see whether your canvas you can see this assignment? Can? Cannot? Can? Thank you. Okay, so we're going to start this week. So if I ask you to do it by next week, there's no way we can do it, right? If you submit this by next week, can or not? No, the problem is, it's fine. The problem is, if you don't submit by next week, that means we will submit it here. When is Chinese New Year? Yeah, so we do it before. No, if I do it after, it will be more problematic for you. Actually, what I prefer is, normally I submit before Chinese New Year. Then during Chinese New Year, you all can go and try the module, the abacus during Chinese New Year itself. That way it's easier for you all. Huh? Okay, so let's fix the date. Hello. Let's fix the date. We all prefer, if I do it here, so we're going to go through a little bit next week. We spend normally 1.5 weeks for the calculation part of it. So the second half of the week, I will do a little bit of the introduction of the abacus, right? Okay, wait, let me just write it for you. I'm going to write on the board the way that I normally do this. Hey, your lesson is can you check for me? Your lesson is supposed to be 27, 3rd, 17, 2nd. Can you check for me? Is it 27, 3rd, 17, 2nd? Then there's one virtual class one, right? So there's 5 lessons.
Yeah. Yeah.
Sixteen is the virtual. Is it or is it physical? Is it physical? Okay, good. So there's week 1, that is the same. Week 1. Small, sorry. There's one virtual one is when is it? 23rd. Hey, I'm going to write. Hey.
Sorry. 26. 26.
26, 29, what?
What's your one?
So it's week 1, week 2, week 3. Or should I do it on the screen? It's easier for you. Okay, so this is the schedule one. So today we definitely need to start to do the calculation. Okay, that's why you need to try the first lesson, the first assignment. Then after that, we will continue to see whether you have any problem. Because beyond the typical thing, right? Then you just in case you need the help on the assignment. So that's why this weekend you all must go back and try out the assignment 1 already. Okay, if not you will not have time. Okay. So it's something new. That's why you need your effort to go and try it during the weekend. Then next week, right? Second half, I'll spend half a lesson to go through the assignment in case you have anything you want to ask. Okay. After that, we go to Abacus, show you a little bit of how the software works. Then we go to the beam model to show you one case whereby beam model is like a single element type of model. After I go the week after, beam element shell model, last one is a solid model. Okay. I showed you the assignment 1 just now already, right? Everybody can see, right? Give a feel of assignment 1. That is why you need to do it this weekend. Okay, this assignment 1, look at it. Okay, so but don't worry, by the end of this lesson, you will be able to at least answer 3 of the questions at the minimum. Okay, so this assignment 1. Show you assignment 2. So this is assignment 2. At the end of assignment 2, right, you're supposed to reproduce something like this. Okay, you're supposed to build a 3D model for this. Okay, so imagine like I say, you've got to be very independent to learn the software on your own. Okay, that's why like I say this module is definitely, in my opinion, more rigorous than a lot of your module. Okay? Later, I will show you some of the past assignment. Later, I will show you because I want to set the expectation right at the beginning. Okay? I will show you the 3 assignments that we have in the last year, so you know what the expectation. Okay?
Is that sample file shared to us?
No, of course not. No, but I need you to understand because, like I say, you've got to be independent in this module to learn the software on your own. If you don't do that, you expect me to go through with you on how to use the software, okay? Then you will not be able to produce what the class here does. And never mind later, you just let me go, just bear with me. Like I said, I want to set the context right first, okay? So bear with me. So this is what you're going to have. This year, the assignment 2 is even tougher than last year, okay? So this is what you're going to do for your assignment 2. Let me show you what they did last year, okay? So this is last year for the assignment 1, okay? By the second week, you must be able to do this already, okay? This is second week, that means next week, okay? This is assignment 1. Last year, there's 3 assignments, okay? Assignment 2 is on the beam. You see, assignment 2 is on the beam and the truss model. Assignment 2 is on the beam and truss model, okay? And the assignment 3 is on the plate and the shell and the solid model. Okay, so I'm going to show you the beam model first. But this year, what is different? This year is the beam, shell, the solid all rolled into one model on its own, okay? But, like I said, more challenging, so hope you can appreciate where I'm coming from. never mind. Later I will show you because normally I do it from the laptop. So I couldn't connect it today. But later I'll show you the expectation for it. Okay. So first, I 5:30. So we will do a quick intro on this abacus first. Okay. So abacus, what does it? So not abacus. Finite element. So finite element, what does it mean? The main thing about finite element, right? For example, if you have something like a branch, okay, here, you need to design for it, correct? So imagine, right, what's going to happen? If you're going to have a top, you're going to see a lot of stress here and here, correct? You're going to see a tensile here and the compression here, alright? So how do you know how to do it? What does finite element do is to discretize it, break it down into small elements, so you know the individual element. It's a little bit like, let's say for example, if I don't do something like this, let's just do it as a simplified rectangular beam, you do a cantilever moment. Can you calculate the stress at that point? You could, right? Yes or no? Yes, if it is a rectangular beam, correct? Okay, 1/16 pH cubed. That is your second moment of inertia. Okay? Then you can get your elastic modulus, your plastic modulus, determine what's outermost fiber stress. Correct? The problem is when it comes to something complicated like this, okay, with a little bit of chamfer, with a little bit of chamfer, with a little bit of groove, then what's the problem? Then you have different stress. It wouldn't be such a simple rectangular beam. So you need to discretize it, break it down into smaller elements. Okay? Finite element does a lot of things. Also things like when you calculate something, when you want to calculate something like very dynamic, you have a ball punching through a plate, correct? Then there will be stress concentration. And finite element also help with that, which you can't do it by hand. You wouldn't be able to simplify it. Okay? So you use in different things. You need to come up with a way to simplify it in order for you to explain it. Later you will see a lot of different model. Okay, if you see what we are doing in this course, right, is the very introductory course. So all the problem that we are solving, right, is your stiffness in terms of your force and your displacement. Okay, but really the finite element engine, right, works for a lot of things, like your temperature, not just the force and your displacement, not only on that, but you solve for other things like, for example, your thermodynamic, okay, your heat flux and your temperature gradient. It also serves for that. The same model could be used for different type of analysis. So even though we are only going through the very basic one, you can know that the same model you build, right, can be done for thermodynamic. Okay, if it is correct, you can also be done for fluid. Okay, like your CFD, it could also be done for that. Okay, I might have a few examples to show you based on my past work itself. You can also do it as a coupled type of analysis. Okay, whereby you have both your force and your stress together with thermodynamic, the coupled analysis, or you could have your thermodynamic and model coupled with your CFD. You can do that also. Okay, so the same model, you can it doesn't just solve for that, but you can solve for a different range. That's the same. I'm trying to articulate it's the same engine. Okay. Yeah. So why do we need finite element? So imagine just now we talked about a rectangular beam. If I apply a force, correct? Let me draw. If I have a rectangular beam, correct? Apply a force. I want to determine what is the stress at the end of the cantilever beam. Easy, correct? I just take 1/16 pH cubed. Okay, that's my second moment of inertia. Correct? Determine what is my elastic modulus, my plastic modulus. I know the stress. Correct? Are you familiar with this? We're going to use a lot of this. Okay, we're going to use a lot law, all these things. Okay? So, if you don't understand, you must let me know now. Okay? So correct, then you know your force, okay, you have a force, you have your length. The problem is, all these things, I expect you to know one. Okay? Like for example, first lesson you will know, have you done matrix multiplication before? Okay? How to do transpose. How to find an inverse matrix in Excel file. Don't do it by hand, for goodness sake. Do it Excel. Okay? Confirm will not go through. YouTube, go on YouTube and go and find out how to do it. Okay? So like I say, require you to be independent. I recommend you all to do Excel because when I mark, I use Excel to mark also. Okay, you want to do by hand? No way. Okay? Anyway, that's why I say I need you all to be independent on this. I know my moment, M equals to F, L, correct? My stress equals to what? Moment, okay, divided by my elastic modulus. That's it. I know the stress for my cantilever beam here and here. Agree? Yes? Do by hand, no problem. Come to something like this. Can you do it? Okay? If it's a beam and a force, I can do it just not the same way. If something complicated like this, I can't do it. Correct? That's why we have finite element. Okay? So what happens is that I'm going to discretize. That's right, in finite element, right? The main thing about it is discretization of this very complicated body, correct? I discretize it into individual blocks. Correct? So imagine now I am trying to do is really a force coming in on a small rectangular section. So it becomes less complicated. Okay? To make it something more, discretize it is to give it a more regulated type of formation so that you can determine the stress on this. So actually, if something like this, right, essentially imagine what is going to happen is I have a force onto two blocks and they are restrained. Is that easy to do? Much easier. Correct? Correct? Yes? Yes, yes? Yes? Okay? So discretize it, make it simple, break it down, something more regular so that you can actually solve for it. Okay, that is what we need. And in finite element, right? Why do I say just now? The model you use is, the engine you use is always the same. It's always the same model. You put in different governing equation, which I'm going into a little bit. Okay, you put in the different governing equation. Okay? But the model is the same. The model is what? The model is a shape function. That means every one of these the cubes, right, or the square or the cube, square in a 2D, cube in a 3D format, will have the same shape function. Okay, and you can have different type of element for different type of problem. Okay, which you will also be very familiar at the end of the 6th week. Okay, all of them. Okay, 50% of them will be covered. For example, like what? For example, like your beam and truss model, you will know. Okay, like your shell model, your membranes we will not do, but shell we will do. Solid we will do. Rigid, this with beam element we will do. Rigid we will not do. Infinite definitely not. Okay. You have different model for different condition. For example, you all know what's a, okay, never mind. When we go there, we will talk about it. Okay, this is a shape function. Yes, yes, yes. Okay, so you have different shape function. We will not go into the theory until we go to that. Today, like I said, I will first give you a brief intro in finite element. We will start with assignment 1. Okay, so that weekend you can go back and try. Okay. Why? So this, huh?
Easy.
Sorry?
Easy.
No. Hey, wait. It's not going to be easy. I'm not trying to pressurize you. I'm just telling you for the fact. every year at the beginning of lesson, I let everybody know it's going to be quite rigorous, this module. Okay, but look, every year, everybody does it, all right? Okay, most of the time, most people pass. Okay, so don't worry. Okay? But I need to set the expectation right. You know, things like, for example, I told you, you're going to burn your weekend for sure. You are going to be independent and going to learn how to software, going to learn the Excel, you know, and remember how you do your student matrix, things like this yourself. Okay? I will go through it, but I will not repeat it. I will expect you to know. Okay? Can? So this is the shape function. Okay, so every one of them, right, uses the same shape function, which is a stiffness matrix. Okay, slightly different from the normal stiffness matrix that you do, but generally you just need to know that all of this is the same. You're not going to be tested on it, just for you to appreciate it. Okay. So the shape function, what does it mean? I'm also not going to theory. I'm not going to the theory on. Let me think whether should I go to theory. I'm not going to theory for this until when I show you the brief intro on the software. I will go back to this. Okay, I'll come back to this later. Okay, this. So just now we said the shape function, right? So this, everybody know, who do know about what is a stiffness matrix? When you do your structural analysis, who do know a stiffness matrix? Don't know. Confirm don't know. Okay, never mind, later. Okay, so you have the same stiffness matrix. That means it's a resistance. Imagine your Hooke's law. Okay, remember your Hooke's law? Imagine your Hooke's law. What is it? It's your EA over L, correct? So you have a spring stiffness, correct? Your K is how much force you push it in. Then how much displacement you're going to have based on the Young modulus of your spring, correct? So that is a stiffness matrix. When it comes to what? When it comes to tensile or compression condition. When it comes to bending, is a section modulus, alright? So this is always the same shape function depending on the job. It's geometry dependent. But just now remember what we say, the model can be used for your thermodynamic, it can be used for your fluid dynamic, it can use your normal stress analysis. The difference is imagine if I'm doing a force and a stress model, correct? Just displacement and force. I'm looking at what? I'm looking at displacement and force. Okay? Then my property, right, will depend on the stiffness. Correct? If you're thermodynamic, you use the same model, correct? Your K will be based on your conductivity. That means how fast your model, right? Imagine if I have now in this rod, cantilever rod, like I'm not talking about the force passing through it. I'm talking about if I have a heat sink here, I have a heat source, see how much of the temperature pass through. Okay, then the stiffness is what? The stiffness is your conductivity, correct? Yes. Okay, and also your boundary condition will be what? Your boundary condition will be your temperature. Sorry, your boundary condition will be your heat source. Then your behavior instead of displacement will be your thermal gradient. Okay, you'll be things like the heat source will be things like heat flux, how much force you're supplying in. Then for fluid dynamics, same thing. Now instead of conductivity, how much the heat transfer through a particular body, correct? Now we're talking about viscosity, how fast the flow is going through it. So it will be the viscosity. Something viscous and something less viscous like water. Something very viscous like your gel. Can you imagine how quickly it flows? It will be based on the viscosity. Alright? Then it will be based on your velocity and your body force, which is your pressure. Okay? So using the same model. Now, this is where we start. Everybody will start to take out a piece of paper. We're going to start. Okay, with some practice already. Rough paper. Come here, there's two things you must bring. You must bring paper, pen, laptop. Okay? Or I will ask if we can have a computer lab for next week or not. But you will need it. Okay, if you can get it, you will need it. Paper and pen. Why is paper and pen? I work as a I work as an engineer. So every time we solve any problem, always pen and paper to draw the diagram. Okay, this is how engineers communicate, correct? Through your diagram, through your drawing. Isn't it? Be it whatever domain you are in, it's always through drawing. Financial accountant through your books. For us, it's really through your diagram, as your engineering diagram. Okay? So just now we talked about stiffness matrix, right? Hello. Okay? Can. If you all need me to stop, let me know. But I have a certain idea where I'm going to stop before I give you all a break. So I need you all to bear with me. Like I say, my objective today, we must start off with the first two questions in assignment 1. Okay, if you wait until next week, you will okay. Okay, so I need everybody to work with me. Now this is a statement matrix. Okay, imagine I have two infinite element, right? We call this, right, the nodes. These are nodes, this is the element. Okay, so when we start off, is very first one we start off with always a linear element. Okay, means what? Not a linear element, 2D 1D element. We always start with a 1D element. No, 2D element, you're right. It's a 2D element, okay? So my fault. We always start with a line. We always start with a line element. Okay? This is the first thing to do. Just now remember when we talk about this, right? This I need to visualize a little bit. Why is it important? So just now we talk about the discretization, right? Same thing, if you talk about a beam, right? If I have a beam, correct? 3D beam. Same thing, we start with the easiest one. Cantilever beam subject to a force, correct? I can model it as a 3D feature. Okay? Alternatively, I can model it as a single element. Correct? The other way, I can model it as a projected plate. Okay? Okay? It can be modeled as a projected plate or as a single beam model. Or as a solid itself. What is the difference? What is the difference? Okay? The difference is, just now remember we say, our main aim is to discretize this, correct? This is something that it's good that you can visualize this at the beginning. Remember we say the finite element is really about discretization, correct? I want to find out the individual cube in the 3D model, how much is deformation for the load, correct? So I'm interested every node, okay, every cube, what's the force under this force here, correct? Yes, correct? It could be in all three directions. Okay, it will be all three directions. The stress will be all three directions. Agree? Okay? When it comes to the plate, same thing, I discretize it. Individual plate. Now, the plate, right, will only have two directions. Correct? This direction, right, it will be linearized. That means I don't really see, because I don't have a node, so I don't know how it evolves. I can only see how this plate bend, how it elongate, how it compress, but I don't see how it is compressed in the thickness direction. Yes? Correct? Assuming this is your x, y, and this is z. I can't see the z direction in the plane. Correct? For this, okay, I can only see the individual element, so it's only a one-dimensional. Okay, a single dimensional. So I only see the x direction. This I see the x and the y. Okay? Why? Because when it comes to your computation, correct? Let's say for example, if I have a beam, I want to know how much compression it has, right? If I break it down into a single dimension, I only need to care what is the deformation in this direction. Okay? So that's why you see just now when we go back to just now our schedule for the assignment, right? You see that we go into the beam first. We go to 1D, after we go to 2D, after we go to 3D. Okay? Can? So you all see where the flow is. So we start with the 1D one. And today we're starting from the calculation for the 1D. Because that's the only way you can do it. You can't do for 2D, 3D, it's going to be too complicated. Okay? So you're going to start with the 1D. Later you will see why you cannot do for the higher order one. Okay? So now I have this 1D element like this here. Okay? I will push it. Just now we say you have the same, just now we always say the stiffness matrix, This is the matrix. So what is the matrix? It's linearized as a single coefficient spring stiffness K. Alright? So imagine this node is free to move, and it can also exert a force on node 1. Correct? Remember two things. This node is free to move. Correct? And you can also apply the force to it. Okay? Likewise for node 2, it's free to move. You can apply a displacement to it. Alright? So imagine if I wanted to know what is the force at 1, at this first node, what is the force? So what is the force? It will be K multiplied by U1 minus U2. If let's say for example, if I restrain this node, if I have a spring, if I restrain one end, now this is the spring. This is node 1, this is node 2. If I restrain node 2, I apply a force on it. Correct? U2 equals to what? 0, correct? U1 will be the force, will be the displacement, correct? So if I know that the displacement is 1 millimeter, I can back derive what is the force. So it's 1 millimeter and my stiffness matrix. That is the force I need to apply. Agree? Now, if U1 and U2 is equal, let's say now U1 move by 1 meter, U2 I don't restrain it, it also move by 1 meter. So what is the force on F1? 0, correct? So imagine if both is not restrained, you push it, it will just keep on moving. Correct? U1, U2 is free to move. So that means to say what? The force is the amount of force generated is the amount of force you need to overcome the inherent stiffness in the body. Correct? Correct? If both is not restrained, there's nothing you are overcoming. Okay? So that is why it's called a stiffness matrix. Alright? Same thing for U2, for F2, okay? It will be U2 minus U1. Okay? And you see the sign convention. Okay, there's a few things that this is important. I want to orientate you. Every single question that you have, right? First, you must denote. We will go through a few rounds only, but I just want to bring this up first. There's a few things you need to remember. You need to mark where is your node. Okay, node 1, node 2. What is the element, which is your stiffness K? Because you could have a series of springs, they could have different stiffness. So you need to denote that. If not, the sign convention is going to be wrong. Okay? For example, a tensile force is in positive. Compressive force is negative. Correct? Here, we're not doing mathematical calculation. To me, the value and not just the magnitude is important. The sign convention is important because I need to differentiate between what's the tensile force and the compression force. Okay? This illustrates as an engineer, your understanding of the problem. Okay? So this is important. So in order to do that properly, you need to denote them. Alright? Okay? Note 1, note 2, you also need to denote what is your direction for positive. All these things might sound foreign to you. I will drill a few times and you will understand. Okay, later we're going to we'll get everybody to come and do the trial question one, so don't worry. Okay, I will drill a few times. But I want to orientate you. Alright? Can? So U1 left to right is positive, okay? Always left to right is positive. Like I said, this is important for you to be able to make sense of your sign convention at the end. Okay? So imagine this is the formula that we have. I put it together. Your metric calculation. Imagine okay, this K, negative K, negative K. Correct? This is a standard one. Later you will see, and I told you just now, right? The shape function is the same for every type of model you put in. And you will see later, all the elements, when we come to a different type of spring put together as one big border itself, they always follow the same form. It's the principle for finite element. Okay, just like Xiongmei. Of course, the Xiongmei is a little bit different, but the idea is the same. Alright? Put this together, so it's what? K U1, negative U2, K, alright? Negative K and K. Put together, this is your Steiner matrix. Okay? Can? Everybody can write this down? This. A little bit of repetition. So is the load is a vector. The displacement is also a vector. Vector means that it's not scalar. That means it's not just a magnitude. It's not that you're not just concerned with the magnitude. You're concerned with the direction. Okay, so they do have direction. So note the sign is important. Now, just now we talk about this. One force, okay? You have one element. This is our Steiner matrix, correct? This is what we talked about just now, right? Everybody remember, right? It's same, K negative K negative K. Okay. Now, if you have two spring in series, correct? So generally, it's the same with that. So just now, remember we do the first one, the first beam, correct? Our first beam, 1, 2, correct? Then we say we need to denote U1, U2, K1. First element, stiffness is K1, alright? Steiner matrix, okay? It will be F1, F2, K1, negative K1, negative K1, K2, U1, U2. Correct? Same as what we did just now. Now, another element comes in. U3. Correct? Okay. What is the Steiner matrix for this second element? Hey, my apologies. So let me do it better so I don't confuse you. One, two. Okay, so this is U1, U2, K1. First element. Second element. 3. Okay? Now the second element is K2. You have a different stiffness. Okay? It could be a different stiffness, it could be something thicker, it could be a different type of material, you know. So the stiffness could be different. Stiffness is not stiffness EA over L, correct? Okay, so the stiffness is generally EA over L, correct? You have same material, still material, but larger diameter. A will increase, so the stiffness will be larger, correct? Shorter, lighter, different material. Let's say you go from a copper, aluminum young modulus to a steel young modulus. The steel will be higher, so that's why the stiffness will be different. Alright? Okay? Okay? And if you all got anything to ask, can feel free to interject. Okay? So F2, F3. Okay, K2 minus K2, negative K2, K2, U1, U2, U3. Correct? Agree? Yes, yes. Sorry, something. I'm sorry, sir. Can I see? Can? Okay. Put these together. Okay? Yes. I can't hear you. I can't hear you. Sorry?
K2.
Why?
Think about the matrix K2 or K3.
It doesn't matter, it's just a notation. It doesn't matter. So you're right. That's why that's the part that actually you can. That's why it's important for you to name it. When I will look at your diagram, you will put K3 here, I need to put K3 here. I will look at your diagram, that's why you must always draw. Okay? Whatever problem you will see, even if you do your model, I need you to draw. Okay? Even when I do it myself in my real life work, I draw. That is how engineering demonstrates a principle. Okay? Like I say, this is not a mathematics course. My intention is for you to demonstrate your engineering application. Your how to say? My intention was for you to demonstrate your engineering understanding of the problem. Okay? In the event, if you don't know how to calculate, you just draw a diagram for me. Show me you understand how this is supposed to be done. I will still give you mark. I'm a bit serious. If you have nothing, you just write a matrix for me. I confirm will give you 0. If I show that it doesn't show me that you understand it from an engineering understand. It doesn't show me that you have an engineering appreciation for the problem. There's no way I can give you mark. Like I said, this is not a mathematics question. Likewise, when we go into the software part of it, I will test right. It's not a software, okay, module also. Okay, it's for you to demonstrate engineering understanding or your engineering appreciation of the problem. So it could be done in different ways. I'm trying to say it could be done in different ways, but you must look at it from an engineering, as an engineer, from an engineer lens, alright? Okay? Yes. It's okay. Give me, when is the lesson? 6 o'clock or 5:30?
5:30.
Normally what time you have break?
Halfway through.
Huh? Later you will see why I need to rush this. Like I said, I need you all to try this. Just give me a minute. Okay, so I put this together. So if you want, hey, continue. Can somebody just tell me what you put together? Okay, so my degree of freedom is what? U1, U2, U3. Correct? Why? Just now we say, correct? If your body now, the nodes is where is free to move. That's why in engineering, as a finite element engineer, we always call this a degree of freedom. It's free to move. That's why it's called a degree of freedom. Okay? Then this body here, right? One whole element. It can only move at the front because I define it. Okay? Remember we talked about the discretization? Okay? I draw the square like that. Okay? I draw the square like this. The plate like this. I'm saying that this node can move, this node can move, this node can move. That's all. Okay? I can further discretize it, but now I only define it as 2 elements. Correct? So only these 2 nodes are free to move. Okay? How many you should draw? We can talk about it when we build the model. But at this point in time, I just want you to understand that. Okay? So in this body, there's 2 elements. Each element, front and back, free to move, degree of freedom. Node 1, node 2, node 3. U1, U2, U3 because they are free to move. Correct? And on top of that, at each node, you can apply a what to it? I heard somebody say something. Force. Okay? So it will be F1, F2, F3. Correct? The stiffness. What is the stiffness?
K1.
Okay? You put this together, correct? So it will be okay, F1, F2, F3. Put this together, okay, it will be K1, negative K1, 0, negative K1, K2. Sorry,
K1.
K1. Very good. K2, negative K2, negative K2, K2, 0. Okay? Can put it together. You see that? Okay, like this. Do you see that? This is 1, this is the second one. Right? Okay? So imagine if I have a lot of elements. Okay? Do you see that now? All of them all of them have the same form. Correct? Even though have a different K to it. But the K you think about it, it's just multiply it one time. You know what I'm saying? You just multiply one time. It's the matrix multiplication that is computationally expensive. but I just multiply the 2. Let's say a k is 2. This is 1, this is 2. It's a very linear type of multiplication, it's very fast. But imagine you want to do a matrix multiplication to this, or a matrix inverse to this. Do you imagine the amount of work to be done? You see what I mean? That's why this is called a shift function. Huh? And okay. This is where you come in. Everybody take a pen, or pen, paper. Now it's for you to do. Okay? I want you to build the matrix for this. Okay? Nothing complicated. What did we say just now? Hello. Does it look daunting? Yes. So what are we supposed to do? Remember what we do here? I don't care about any of these things. I number it. I do it as one element at a time. Remember when we do this here? Element 1, element 2. Do I care about element 1 but I do element 2? No, I don't. I write down for individual one of them, then I combine them together. Do you know what I try to say? Yeah. Okay, for example, element 3. Okay, what is the degree of freedom? How many degree of freedom does it have? 2. Very good. The first node is what?
3.
U1? U3, very good. Second node?
U4.
U4. You see what I mean? So F1, F4, U3, U4, F3, F4. That's all. We do for individual element, then we put it together. Alright? Come. I give you 10 minutes. I will get people to come out to write every year. Ten minutes, Hey, just now we say, right, as an engineer, what's the first thing you do? Draw the diagram. What diagram are you supposed to draw? Okay, you draw the entire model, then you denote each one as U1, U2 for each of your elements. Okay, which the force, what is the stiffness. Okay, so you draw. Later you see the assignment, you get what I mean. Because this is drawn for you. Later when you see the assignment, you get what I mean. But this is what you're supposed to draw. Okay, and everybody draw this. Then write down the standard matrix for individual element first. Okay, and I will get what? 5 people to come out to draw for each element. You all see from here, so basically you want to see method. Okay?
Draw the whole thing.
Oh, draw the whole thing.
Draw that line. No. You have more space lah. Draw the whole thing.
You get what? Because you will need to do this for your assignment.
这个话我是觉得一个一个可以了，因为你最后要 X 把其实全部也可以，我觉得，把会要想很多啊。
Therefore, F2 and K4. Yeah. I think you combine 4 and 1 and I can do this. So before I take it more sure what I can do.
When you're not wait, sorry, just a minute. This one. Yeah, the same thing. So you just do it as an individual element. Yeah, so you don't need it's actually the same thing, you know. It's just the denotation is different. It's doing exactly the same step. Just change your 1, 2, F2, F3, just change that R. So we do the individual element, don't need to be daunted by so many elements. Just put the individual one, then later put it together. Okay? There's a method to it, but you can't do that. Yeah, for example, let's say for the first element, right? So the first node is what? Correct. U1, U2, correct. So we just do the first element now. So it will be K1. Correct. You just look at this one. You just look at this. Yes. Then that's a good point. But that was a good point because later I'll explain. But actually it doesn't matter because when I look at this element, right, I don't care what's happening here. I'm just looking at what I'm going to overcome here as an individual element. Okay? Rather than the entire. But you are right, it does overlap. When we put together, then you will see that when I move, in order to put this, in order to move this node, I overcome this and this, but you're right. But that's why when we are looking at the individual element, I don't care what this was. Yeah, but you're right, you're right. That's why it's, then that is why the status matrix comes in. Yes, sir. This. We're going to go through this, then we're going to go through assignment question. Okay? So as I cover I use three. Hey, class. Those that have done already, right? Those of you trying to examine the actual work with matrix. Okay, now on your own, you have the first example them as a matrix. You know, it actually starts nothing special. So on the one hand, it will be what? It will be what we have there: U1, U2, U3, U4, U5. At the end of the equation, you F1, F2, F3, F4, F5. It doesn't matter, right? So we just take all the K based on U1, U2, and example them as a global matrix. Okay, so can you try?
或者说听不懂，或者说听不懂。被区分。我在看这一种。I mean, K4是241。I believe 要 plus. I believe this is like K4 plus K2 K3.还是 OK 没有错，应该是可以去，这个应该是，这个也是错，这个也是错，这个怎么可以？它上面写错了，反正这个应该是 K1，这个是 K2。
Hey, class. Huh? Sorry?
Your first matrix, your K1 supposed to be everything K1, not supposed to have the K2 inside.
F1, F2, bracket K1 negative, K1
Your first equation, the red color one.
This one is K1, yeah. This one correct, K2 lah. Hey, I'm too old for this, seriously. Every year I jump a little bit lower. First year when I taught this, very energetic. Now I'm a little bit too old to struggle. But this class is slightly larger than last year. So, can you all cooperate with me? Everybody ask the same thing, which is good. Because like I say, it's your understanding of the problem, which is absolutely good. But because everybody asking the same thing, so give me a little bit of chance to say this. First, typo, K1, okay, which a lot of people noted that. Very good. Now, everybody asks the same question, which is good. So imagine, I'm much older than many of you, so can you all be kind to me? Okay, see when I want to displace node 1, look at this little matrix. I'm going to displace node 1. What spring do I need to overcome? K1. When I want to displace K3, and you node 3, which spring do I need to overcome? K2. Very good. The problem is when I want to displace node 2, what spring do I need to overcome? K1 and K2. That's why this is the Hooke's law, whereby you assume a linear, which is not always the case. Okay, which is not always the case. You assume both for your elastic. Delta F. This is your Hooke's law. Okay, for both your compression. This is your tension. Correct. This is your compression. Okay, for both your tension and compression, you have a single linear spring constant. Hooke's law, correct? Not always the case. You press it and you pull it. Is it always the same tension? No. But Hooke's law, because in Hooke's law we are doing a spring, it is the same. That's why now you see when I display this, right? K1 is in tension, K2 is in compression. But in Hooke's law, we assume the same. So it's K1 plus K2. Okay? So do you get it? Okay, which is useful when it comes to here. This node here. But then let's do it one at a time. I will keep this because I think this is good. Everybody can refer to it. But let's build up the global matrix. Okay? I will bear with me. We will go through this, build the global matrix. After that, we will look at the assignment 1, question 1. Everybody, can you all access the assignment 1? All can. Okay? Then we look at assignment 1, question 1. Then you all will try for 5 minutes, then you all can take a break. Okay, so we are nearly there. Okay? Let's look at element 1. Hey, class. Is this correct? U1, U2, K, okay, correct. Very good, you see, very good. Listen to me. This is the denotation I want to see. U1. Very good. Denote what is positive. Okay, left to right positive. This is important. You in your assignment you will see why. Denote the degree of freedom, denote the node, denote the element. Stiffness, very good. This one, add in the positive displacement. Okay, F2, F3. Okay, like I say, okay, in your assignment, in your exam, you never put in the sign convention, positive, negative, wrong, because it's engineering. You're not doing mathematics. You're not doing calculus. Your positive, negative is important to me. Number two, unit, millimeter, meter, kilonewton, newton, all is important to me. You may tell me that kilonewton and newton doesn't make a difference. It's 1 ton and 1 kg. Does it make a difference? Yes, it does. As engineer, especially important. Okay? So all this will be important, huh? Okay, is this correct? Okay? Correct, huh? Correct? So at node 2, I only, at the U2, U3, is this element, I only overcome this. Yes, as a global matrix, if I push this, I will need to overcome this force. But then, I'm only looking at this element now. Correct? So I'm only overcoming this. That's why we're looking at the individual elements matrix before we put them together as a global matrix first. So don't need to think too much. Okay? It's actually quite simple so long as you start to get familiar with it. Alright? Element 3. Okay, U3, U4. Very good. Okay? Element 5. Right, this is 5. Yeah, never mind. Okay? So element 4 will be okay, right? F1, F2, F4, K4, negative K4, negative K4, K4, U2, U4, very good. See? Everybody gets it now. So long as you start to get familiar with it, it's actually very simple. Alright? Very good. Huh? Let's just build this up. I think it is worthwhile for me to do it here with you. All this doesn't matter anymore. Okay, only this. Do you see that? Only this is important. Do you see that? So if you what? U1, U2, U3, U4. Is that all?
U5.
Very good. U5 equals to F1, F2, F3, F4. Will that be your F5?
Yes.
Correct. You will see that in this kind of cylinder matrix, right, it will always be symmetrical. Okay, so that you can inverse it. If you do, when you go your Excel cannot inverse, that means you got calculation error for sure. There's no way it will inverse because you see it always starts with K, negative K, negative K. Okay? Likewise, the number of degree of freedom will be the same number of force. Okay? External force. Okay, so now it's very simple. Let's look at U1. So what you do one, you do this. Okay? One by one we example that. Okay? Okay, same thing. So this is what? This is U1, U1, U2, U3, U4, U5, U1, U2, U3, U4, U5. Okay? So U1, what is it? K1. So K1. Okay? After that, 1. Negative K, 1. Negative K, 1. This is this. Correct? Yes? So this is done. Can? Next one. Let's do this one. Okay? So this K2 put in where? Tell me column what, row what?
U2 U2
Huh?
U2 U2
Column 2?
Row 4.
No. Column 2 what?
row 2
Row 2. Always column 2, row 2. You know, column 2, row 2, column 2, row 4, column 2. Then it's going to symmetrical ma, huh? It's okay. Okay, so it will be what?
plus K2
Plus K2.
minus K2
Okay, then the next one. This one.
minus K2
Which row, which column?
3 2 3
Huh?
row 2 column 3
Okay. Negative K2. Negative K2 plus K2. Agree? Agree? Now, so this is done. Okay? Which one should we do? Shall we do this one? We should do this one, huh? Because this is where the overlap. The node 2 is the overlap. You see node 2. How many spring should you see? How many K should you see at row 2, column 2?
3
3. Very good. Okay? So this K4 go where?
row 2 and row 4
Okay. So it's plus K4. Okay? Next one is where?
row 2 row 4
Row
row
two
2
column?
column 4
Column 4. So it should be negative or positive?
negative
Very good. Negative K4. Okay? Negative K4 plus K4. Agree? Do you see just now we mentioned about this? If I move node 2, I will mobilize K1, K2, K4. Does it make sense? Okay? I will not waste your time. You all need me to run through everything? No. Do it. We got 5 minutes. Then we will take a break. Okay? 5 minutes, You all take more than 5 minutes, then makan your break, not my fault, Okay? Then I will get someone to fill out the whole thing. Okay? Wait. Shh. Okay? Be kind to old man. 5 minutes time, I will get someone to fill it. Once we got it, we can take a break. Can? I did my postgraduate, I did my master, and I did my PhD all part-time, so I can totally understand. One of my motivations is because I see that it's not easy as I thought it was. I feel that it is my way of helping my understand such so I appreciate. I understand. First, I understand as a student adult during your degree part-time path. Totally understand. Okay. Okay, if anybody got it already, can you raise your hand? Then we can all take a break. Go. Just go. Hey, we don't have time, Hey, guys, hurry up. We don't have time already. 5:30, right? So imagine we must. This is the simplest question, Your assignment later, I will flash it, then you will know what I mean, Okay.
应该对了，应该对了。我的有点乱了。
Everybody agree with this? Okay. Wait, I promise I will excite you to come back after your break. Let's look at assignment 1. Okay, I want everybody to draw. Then write down the denotation and what you have done just now. Okay? Draw. How many questions you all want to go through for today? All of it. All of it, I'm okay one. All of it, you all say all of it,
Can I got as much as
all of it, depend what time you want to stay back, okay? Hello.
trying my head
Draw. Then denote. What do you denote? What you are drawing now is what you will submit. Is as good as you are submitting to me. Or I promise I'm going to find for you the. I'm going to find find for you that this assignment, what they did last time, right? Okay, you all draw, then I search on the side. Don't care about the. Don't care about this the number first. Draw the figure, okay, and denote the figure.
也是要一个一个画。
Same thing. Once somebody got it, erase that side, then draw on the board.
Okay lah.
K1 I think 你可以 separate 也可以 but 因为那个 matrix 会 lead 你 to the same table 也是，所以 I think 你 let's say 你 separate 哇，等一下哦I believe 你放在一起，你跟你分开啊，你都会拿一样的。因为你看 ，let's say 我分开 right， 我会拿这样子。所以如果在里边呢，我 combine to，let's say 我先 combine 先啦，你会拿like example F1 F2， then 你应该会拿 K1 plus K3 minus K1 minus K3 minus K1 minus K3 跟 K1 K2， 所以 at the end 你还是会在那个 table， 你还是会拿到其中这个东西，所以你现在 combine 跟 data combine 跟 Yeah， 如果你 split up 的话，because at the end the result you will get. So I think it's better 你 follow 那个 K， 然后那个 individual K。Yeah， 你 just follow 那个 K， then 你 just 放 point 1 point 2。Yeah， at the end 你在 combine 在的 你的 last matrix 的时候，它还是会 get the same。如果你 combine earlier， 因为你 combine earlier， 你还要麻烦去想这个东西要加，but 也不会太麻烦啦，觉得。没有，我 maybe 我会错，我不知道，好像真的很惨。
Okay, just a quick one. Show you the beam one. The beam one is, remember I told you there's two assignments, right? One is the beam. Just now we said the beam 1D. That's what we're doing now, and also the 2D and the 3D. Beam is the easiest. So let's take a look at the past year report. Okay. So what they do, so it's supposed to build a truss for the bicycle. This happened at the third, fourth week. Okay. This happened at the 3rd, 4th week. So imagine yourself, try to picture yourself 3rd, 4th week time doing this. Okay. So you're supposed to design for the bicycle frame, do a frame, the truss structure. Okay. Different size of the element. You're supposed to do up the model. Okay. Then you come up with the displacement for the different element. Then come up with all the. This is the truss model. This is the beam model. Then, hold on. Then you're supposed to compare. Imagine, you're supposed to compare for the different type of element. Steel element, aluminum element, titanium element. Which one is the most conducive? Are you going to use titanium because it's strongest, but it's going to be most expensive? Okay.
Then the material table.
Then you're going to do a check. Okay, you're going to do a check to make sure that the model makes sense. You're going to do a hand calculation to make sure that the model makes sense against your software result. Okay. So this is the easier one. Later I will find you the shell one. Okay. Let's look at another one. So every year I show you to let you know what is the expectation. Okay, every year I show the next batch, the previous batch, what the previous batch do. Okay. So this is another example. Very good. Show me a lot of the thoughts process behind it, you know. So show me that this is the tubular section you are looking at. You know what is the? I need the volume. I need the area. So I know the volume because with the volume I can calculate the cost. Okay. Then the displacement, the force, the stress. Okay, you draw the model. Okay. So you know, like I say, that's why I'm rushing through the calculation because this is what you need to do. Okay. You see now you see my point. Okay. Then you see the displacement. This is the U2 displacement. This is the U1 displacement. That means the force and the difference in this direction. This is U2 this direction. Why does it matter? At bicycle, halfway on it, I want to know how much settlement there is. It brings a comfort. Okay, they call it the compliance check. Alright. Okay, that was it. Now we are doing is this one. Okay, we're doing this one. Okay. Shall we take a 10 minutes break? Okay. So you see why we are rushing through? Okay. Come back 10 minutes. I will start sharply. 5 past 4. Is it very fast? Very fast. But do you see why we need to go fast? Is it fast? But you all see why we need to be fast? It's just like we see like what that's the end of the module. You see, if I do this slow, there's no way I will do this 65. Okay?
Are you going down?
You want to go down?
You guys are going down.